Okay, in today's lecture notes, we're going to look at rational functions a little more closely. So you should recall that rational functions are quotients or ratios of polynomial functions. So they're functions in the form f of x equals p of x over q of x, where p and q are both polynomials. And q of x should not be the zero polynomial. Okay, so the domain of rational functions is all real numbers except where the denominator is equal to 0. So that's everywhere except for where q of x equals 0. So the denominator cannot equal 0 for a rational function. And the reason for this is pretty simple. We already know that the domain of any polynomial is all real numbers. And so if you're going to take a ratio of polynomials, then it's going to be all real numbers except for where maybe you're dividing by 0. So as long as you remember you can't divide by 0, you know exactly where the domain of a function is. Okay. So in example 1, we're asked to find the domain of f of x, which is 2x squared divided by the polynomial x squared plus 4x minus 12. And so what the previous statement tells us is that if we want to find the domain, we need to find all of the real numbers except where the denominator is equal to 0. So we take the domain should be equal to everywhere except, or all real numbers except where x squared plus 4x minus 12 is equal to 0. And then we need to solve for 0. So here again, this is another application of where solving for zeros is useful. It's finding the domain of these functions. Okay, so you can probably see how to factor this, or you could always use the rational root theorem and then synthetic division like we learned last week. But we basically know that the roots are either going to be 12 and 1 or 3 and 4 if they're going to be rationals. And so in this case we have x minus 6, or 2 or 6, right? And so for this I think we get x plus 6 and x minus 2 as our two roots. So our factors are x plus 6 and x minus 2. Okay, and so that would be either x is equal to negative 6 or x is equal to positive 2. And again, to see how I factor that, I'm looking for two numbers that multiply to give me negative 12, and then when I add them together I get positive 4, which is the middle term. So 6 minus 2 is positive 4. Okay, so for the domain of this f of x, we get everywhere except for x equals negative 6 or x equals 2. Another way to write that in interval notation would be from negative infinity to negative 6, union the interval from negative 6 to 2, union the interval from 2 to infinity. And on the number line, it would look something like this. We'd have all real numbers and then an open circle at 6, all real numbers, open circle at 2, and all real numbers. Okay, so now I'd like you to do h of x. I'm going to pause the video and have you answer the quiz question, and then I'll show you how to do it. Okay, welcome back. So now again, we're looking for the domain, and it's going to be all real numbers except where x times x squared plus 64 equals 0. And now we'll solve for where that actually happens. Well, it's either x equals 0 or x squared plus 64 equals 0, which would be where x squared equals negative 64. If you take the square root of both sides, you get x equals plus or minus 8i. Okay, well, the plus or minus 8i is not a real number, so we don't have to worry about this part. So when we're ruling out points in the domain, since we're only like writing down the real points, the only thing that's not in the domain is x equals 0. So I guess the domain is going to be negative infinity to 0, union 0 to infinity. And if you were to plot that on a number line, you could do it like this. You put an open circle at 0, and you're allowed to have any point to the left or right of 0. Okay. So unlike the graph of a polynomial function, the graph of a rational function can have any number of breaks and can be composed of different sections. As we discuss this behavior of rational functions, we will use arrow notation or limit notation. So the limit notation or arrow notation is the following. If we want to say x approaches a from the right, okay, we would write x arrow a, and then we have a plus sign as our superscript. So this is saying x approaches a from the positive side, or the values that are just bigger than a. Okay. And let me do this on a number line. That would be like the following. If this is a, when we're asking, or when we see x arrow a superscript plus, that means x approaches a from the right. That means the x values are approaching that a value from the right. So x is going that way. Okay? If you see x approaches a from the left, then you write x arrow a and then superscript minus, because that's coming from like the negative sign or from the less side. So when you see that, the statement is that x is over here to the left of a, and it's approaching, it's moving closer and closer and closer to a. Alright? The next statement is x approaches infinity. Well, that just is x arrow positive infinity. So when you see that, it's telling you to look at what happens when x gets really, really, really big. So x is going towards positive infinity. And then finally, x approaches negative infinity would be the following scenario. So now x is going to negative infinity, so x is just getting arbitrarily large but negative. Okay, so we're going to use this limit notation to describe the behavior of a function as x approaches some given point. Okay, that's the primary reason for defining this notation. So here is an example, example 2. And I want to look at the green box first. And this is a sentence, right, that we're going to complete. The first part of the sentence says that as x approaches 3 from the right, f of x approaches, and we're saying it's going to be approaching some number. So as x approaches 3 from the right, so here is x equals 3, right? And the idea is that you're supposed to kind of zoom in and only focus on the points that are really, really close to 3 and on the right. So as x is approaching 3 from the right, and we're asked what are the y values of doing. Okay, so we're focusing on this little part of the graph, the part where x is really close to 3 and it's just to the right of 3, and we're asking what do the y values do. Well, if you were looking at this, the y values are going down. Okay, going down and moving towards this y value right there is positive 3. Okay, so almost think of this as like if there was a little ant walking on this curve and his x-coordinate was decreasing to positive 3, then where would his y-coordinate be going? Well, originally, like up here, his y-coordinate would be 8, but as he approaches 3, or as x-coordinate approaches 3, he's moving down to the value y equals 3. Okay? So that's the game that we're trying to play here. So again, the statement says, as x approaches 3 from the right, f of x approaches 3. And again, we're going to do the same thing, and now we're going to look at what happens when x approaches 3 from the left. Well, again, you look at where 3 is, and you look at the part of the graph that is close to 3, and we're going from the left now. So x is approaching 3 from the left. So now we're going to focus in on just this part of the graph, right? So the part to the left of x equals 3. Okay, and now you're asked, what is the y value doing? Well, now it's approaching 3 as well, but it's approaching 3 from below. Okay. And if you wanted to be a little bit more specific, you could say that x is approaching 3 from above and x is approaching 3 from below in each of these cases. But you don't have to. I mean, I usually just say that x would be approaching 3. Okay. Now the next question, the blue box says, as x approaches infinity, f of x approaches what value? Okay, so that means this part right here is telling us to look at what happens when x gets really, really, really big. And you're supposed to look at what happens when x gets really, really big and look to see what the y value is approaching. And the way this graph looks, it looks like the y value is approaching this dotted line at x equals -2. And you could say it's approaching -2 from below if you wanted to. So you could put a minus sign there if you want. But I think the question is just asking, where is it approaching? What value is it approaching? And it looks like y equals -2. If x is approaching -infinity, that means that x is getting really, really big but really, really small. And it's a little bit easier to see here that in this case, again, we're approaching y equals -2. Okay, we're approaching this line y equals -2. And again, it's from below. So if you want, you can put a minus sign there. That's just adding a little bit more information. Okay, what I'd like you to do is try and do this next example. Fill out the red box and the black box. I'll ask you a quiz question on the red box, and then I'll show you how to do it. Okay, so now the red box is asking, as x approaches 1 from the right, f of x is approaching what? So now we need to zoom in on x equals 1, which is, here's x equals 1. We're supposed to zoom in, and then we're only supposed to pay attention to the values of x to the right of 1. So, you know, this function has two pieces here, and the number one question I always get is, which piece should I be looking at? You should be looking at the piece of the function that is to the right of 1. Okay, so that's this piece up here. Okay. And now the question is, where are the y values going as x is moving towards 1? Well, this is a vertical asymptote. You can see that this thing is actually increasing indefinitely. It's going to positive infinity. So the y values are going to positive infinity as x approaches 1 from the right. Okay? So we'd say positive infinity because the function is increasing indefinitely. If I were to ask you, what is the behavior as x approaches 1 from the left, then you would want to look at the y, you'd want to look at the x values over here. So that would be this part of the graph, because those are the values where x is left of 1. And you see that it would be decreasing indefinitely. It's going to negative infinity. Clean that up a little bit. All right. So hopefully that's clear that when you see as x approaches 1 plus, you're saying values to the right of 1. And when we see as x approaches 1 minus, you're saying look at the values to the left of 1. Okay, and the next value says as x approaches -4 from the left, what does f of x do? Well, now you need to look at the graph where x is left of -4. So we're looking at these values, and x is going towards -4. So we're looking at this piece of the graph. And again, you can see that the x values are increasing indefinitely. So here we're going to have positive infinity, because the x values just keep increasing until they hit that dotted line. And then they kind of jump over that dotted line down here to the negative part. Okay. Now we're asked to find the behavior as x goes to positive infinity and negative infinity. So as x approaches positive infinity, that would be the values over here. You can see that the y values are approaching, looks like they're increasing, and they're approaching that line y equals 2. Okay, and again, you could say that they're approaching 2 from the bottom if you wanted to. As x approaches negative infinity, what does y do? Well, as x approaches negative infinity, that'd be over here. Oops. As x approaches negative infinity, the y values are now decreasing. It looks like they're decreasing to the line y equals 2. Again, you could say that they're approaching 2 from above, or 2 plus, if you wanted to. Okay. So hopefully that's clear. We'll do some more examples in class. This next little blurb is telling us, kind of like reporting the behavior that we just saw. So these vertical lines here are called vertical asymptotes. And those are the places where the graph grows indefinitely, either positively or negatively. So let me read that. The vertical asymptotes of rational functions. The line x equals a is a vertical asymptote if f of x increases or decreases without bound. Right? That means that it's growing indefinitely, either positive or negative infinity as x approaches a. Another way of saying that is that y is approaching infinity or y is approaching negative infinity. Okay? And the graph will never touch a vertical asymptote. Okay? It just approaches the vertical asymptote, but it never actually touches it. And then a rational function can have 0, 1, or many vertical asymptotes. Alright, now to find the vertical asymptotes, what you do is you look at f of x as p of x over q of x, and if p of x and q of x have no common factors and a is a 0 to the denominator, then x equals a is a vertical asymptote. So what we were doing in the first part of this lecture, where we're finding where the denominator is equal to 0, that was actually finding the vertical asymptotes. Okay, and then finally, if a is a 0 of the denominator, but it's no longer a 0 when the function's equation is reduced. So this would be like if it's a 0 to the denominator and a 0 of the numerator, so p of a equals 0 and q of a equals 0, then there's a hole at x equals a, not a vertical asymptote. So this last case is where you have p of a is equal to 0 over q of a equals 0. And what that means is that you could have written p of x as x minus a times some other polynomial, and you could have written q of x as x minus a times some other polynomial, and then you should have reduced that. Okay, so if the function can be reduced by factoring out an x minus a, then you get a whole. That's what that's saying. So again, let me write that just a little bit more succinctly. If p of a equals 0 and q of a equals 0, you get a whole. Okay. And so the vertical asymptote is when p of a does not equal 0 and q of a does equal 0. Then you get the vertical asymptote. Alright, so let's look at a couple examples. In example 3, we're asked to find any vertical asymptotes or holes if any of the following graphs. So we have x over x times x plus n. Well, okay, so I'm going to just list the possible vertical asymptotes or holes first. To find those, you set x times x plus 9 equal to 0 and you solve. You're either going to get that x equals 0 or x equals negative 9. So these are our possible vertical asymptotes or holes. And now we need to characterize which ones are holes and which ones are vertical asymptotes. Well, okay, so the numerator here is x. So p is x and q is x times x plus n. So here you just need to say, okay, well, x equals 0 is also a 0 of the numerator. Okay, so in this case, x equals 0 is a hole, and x equals negative 9 is a vertical asymptote. Okay. Another way to look at that problem is you could reduce f of x. So you could reduce this further to 1 over x plus 9 if x does not equal 0. Okay, so as long as x doesn't equal to 0, then x over x is going to be 1, and we could have reduced this. So this would be like f(r) of x or something, like reduced f of x. Could be written like that. So that would tell you that x equals 0 as a whole. But you can't get rid of the x plus 9, so that says that x equals negative 9 is a vertical asymptote. And just to give you a picture of why we're calling these holes and vertical asymptotes is that this function is going to look something like this. At negative 9, this is x equals negative 9, we'd have some type of vertical asymptote. So it would be like something like that, where the function, the y values go to positive or negative infinity. And then at x equals 0, we'd have a hole. And so the function would look something like that. So there's the geometric reason for why that's called a hole, and why x equals negative 9 would be your vertical asymptote, BA. Okay. Now I'd like you to try and do this next one for g of x. So you need to figure out which ones are holes and which ones are vertical asymptotes. So take a minute to do that. I'll put a Kaltura quiz question on there, and then I'll do the problem for you. Okay, so let's start the exact same way that we did the last problem by listing the possible vertical asymptotes or holes. So the only possible hole would be when x minus 12 equals 0. Okay, so this is either a vertical asymptote or it's a hole, and we need to figure out which one it is. Okay, well, to do that you need to figure out if 12 is also a 0 of the numerator. So if I plug in 12 into 12 squared minus 144, that's like p of 12 here, I will get 144 minus 144. Okay, so that tells me that x minus 12 is a factor of the numerator, and so I would have been able to cancel that if x does not equal 12. So this is an example of a hole. Okay. If p of 12 had not been 0, then it would have been a vertical asymptote. Okay. And just as a quick sketch of what this looks like, I think it's a line. The graph of g of x is going to be a line, and it's going to have a hole at x equals 12. And you can plug that into a calculator if you want, and it'll give you a line, and if you zoom in really close or ask what the value is at 12, it'll say undefined. That's because there's a little hole there. Okay, now next we're going to look at horizontal asymptotes, which are actually much easier than vertical asymptotes because there's only 3 rules, and it completely characterizes what the horizontal asymptote will look like. So, okay, the line y equals b is a horizontal asymptote of f of x if f of x approaches b as x approaches plus or minus infinity. So now we're looking for the behavior as x goes to positive infinity or negative infinity. Whereas vertical asymptotes are the places where y goes to positive infinity or negative infinity. Okay, A rational function can have at most one horizontal asymptote. The graph may cross its horizontal asymptote. Okay, so it may cross it. Okay, so to figure out what the horizontal asymptote is, it's actually very simple. You look at your rational function as the quotient of two polynomials, and you look at two pieces. You look at the leading term of f of x and the leading term of b of x, or of q of x, and then you look at the exponents. So if the exponent n is less than the exponent m, okay, then the x-axis, or y equals 0, is the horizontal asymptote. So an example of this would be, an example where this might happen is if you had f of x is x squared plus 3x, and q of x was, I don't know, 5x to the 4th plus 7. Okay? So since 2, n equals 2, is less than m equals 4, so we say, like in this case, n would be 2 and m would be 4. Since the top exponent is smaller than the bottom exponent, you get that y equals 0 is your horizontal asymptote. Okay, so whenever that happens, it's always just y equals 0. If n equals m, okay, so if they have the same degree, then the horizontal asymptote is the ratio of an over bm. So an example of that would be something like 2, let's say f of x is 2x cubed plus 3x plus 7 over 3x cubed plus 2. Okay? So again, all you have to do is look at the leading terms, so those are the biggest powers of x, and now the line y equals 2/3 is the horizontal asymptote, because they have the same degree. So when x gets really, really big, or really, really big and negative, the x cubed terms are the ones that are kind of determining the behavior of these functions, because they grow faster than the 3x or the 2 or the 7. And because it's an x cubed over an x cubed, they're kind of growing at the same rate. So you end up with just a horizontal line, y equals 2/3 as your horizontal asymptote. And then the final case is when m, so the degree of the numerator, is less than the degree of the denominator. Well, that means the denominator is going to grow much faster. So in this case, you get no horizontal asymptote. So the example here would be, the example here might be something like this: f of x equals, I don't know, 3x to the 5th plus 7x plus 2. Maybe the denominator is x to the 4th plus 6. Right? So now the 5 is bigger than the 4, so there's no horizontal asymptote. Okay. So I'll do the first problem here. It says g of x is 15x squared over 3x squared plus 1. So again, this shouldn't be too hard. You just look at the two leading terms, and and because they have the same degree, we're in case 2. So in this case, we're in case 2 because n equals m. And so the horizontal asymptote is y equals 15 over 3, which you could simplify to be y equals 5. Okay? So y equals 5 is your horizontal asymptote. Now this next problem I'd like you to take a look at, and I'll ask you a Cal 4 question. You have to fill it out, and then I'll show you how to do it. Okay. So the only tricky thing here is that 18x squared is the leading term for h of x, so it's written a little bit out of order, but the highest power is the x squared, and the 3x cubed is the leading term of the denominator. So here we have 2 is less than 3, so we're in case 1. So since 2 is less than 3, so that would be like n equals 2, is less than m equals 3, we get that y equals 0 is a horizontal asymptote. Okay.